let us now consider a general case of situation where multiple order poles occur. So, given f of s which is P s over Q s, let s minus s 1 raised to the power of r be a factor of Q f s. In this event, we say that the pole at s equals s 1 is of order r, because this particular factor is repeated r times. Then the partial fraction expansion of f of s will have the form corresponding to the pole at s equals s 1. We can write this as k 1 1 over s minus s 1 plus k 1 2 over s minus s 1 whole squared. So, the denominator will have expanding powers of s minus s 1, and finally, you have k 1 r minus 1 by s minus s 1 raised to the power of r minus 1 plus k 1 r over s minus s 1 raised to the power of r plus terms which involve other poles of f of s, plus terms which involve other poles, that is poles other than at s equal to s 1. Let me call this group of terms as r of s, because we really, our focus now is on how to calculate k 1 to k 1 r. We are not interested in the other terms. So, our discussion will center around methods of finding out k 1 1, k 1 2 or up to k 1 r. Okay. Now, taking the q from the example which we discussed just now, let me say m of s is obtained by multiplying f of s over s minus s 1 raised to the power of r. So, this is the partial fraction expansion of f of s. You multiply this by s minus s 1 raised to the power of r, then this entire group of terms will be multiplied by s minus s 1 raised to the power of r. Therefore, that will turn out to be k 1 1 times s minus s 1 raised to the power of r minus 1 plus k 1 2 raised to the power of s minus s 1 raised to the power of r minus 2 down the line, plus compared to this last two terms k 1 r minus 1 times s minus s 1 plus k 1 r plus this entire group of terms r of s multiplied by s minus s 1 raised to the power of r. That is how this m of s would look like. So, every one of these terms is multiplied by s minus s 1 raised to the power of r, and this is what the result is. Now, it is easy to see now that k 1 r is simply found out by substituting s equals s 1 in this expression, because every term vanishes except this when you substitute s equals s 1. So, when you substitute s equals s 1 in m of s, k 1 r falls out. So, k 1 r equals m of s, which is really P s over Q s multiplied by s minus s 1 raised to the power of r, with the substitution s is equal to s 1. That is quite straightforward. That is k 1 r, k 1 r. Now, to find out k 1 r minus 1, we adopt the same trick as we have used in this example. You recall, we have took the derivative of m of s with respect to s. If you do that, this term drops out, and the derivative of this is simply k 1 r minus 1, and since these are all accompanied by higher powers of s minus s 1, when you take the derivative, they still continue, s minus s 1 continues to be a factor here. Therefore, they all drop out. So, when you have got Tm s over ds, if you do that and substitute s is equal to s 1, then the only term that remains is k 1 r minus 1, because k 1 r disappears, all the other terms have a factor s minus s 1. Therefore, when you substitute s is equal to s 1, that remains, that is k 1 r minus 1. Now, suppose you take the second derivative, then the previous term will come. The previous term here, you recall, it will be k 1 r minus 2 s minus s1 whole square. So, when you take the first derivative you get 2 times s minus s1. When you take the second derivative it will be 2 times k1 r minus 2. Therefore, you have k1 r minus 2 will be 1 upon 2 dms over ds, substitute s is equal to s1. As a matter of fact, this is instead of 2 I will write as 2 factorial because that is how it progresses. This at the previous term when you take k1 r minus 3 you will get in the final analysis 3 factorial, that is how it goes. So, continuing this discussion, it is easy to verify. You can show that k1j is obtained as 1 over r minus j factorial. The r minus jth derivative of m of s over with respect to s with the substitution s is equal to s1. And in fact, you get k11, that is the first term here, k11, and this is in fact called the residue of the multiple order pole at s equal to s1, k11, which is the hardest to find out. It is obtained by taking r minus 1th derivative of dr minus 1 ds. So, in principle it is the same as what we have done in the first example worked out. Only thing is when you have got a large number of multiple order pole, you have to take successive derivatives of this term m of s f of s times s minus s1 raised to the power of r. That is, you knock off the term in the denominator which is s minus s1 raised to the power of r, and the rest of the rational function you take successive derivatives and substitute at every stage s equals s1. So, you get all the terms in the partial fraction expansion starting from k1r right up to k11. k11 is the numerator of the linear factor, k1r is the numerator of the factor s minus s1 raised to the power of r. So, the principle is straightforward. You do not have to really remember these formulas, provided you know the principle that is involved. You can always figure out how it is done. You have to take the rational fraction as such, given rational fraction, multiply by s minus s1 raised to the power of r, and you get a resultant rational fraction function which is called m of s. You take successive derivatives and substitute s is equal to s1. So, the principle of finding out the partial fraction expansion when you have got multiple order poles is again a straightforward extension of what you have done in the case of simple poles, and when you have a combination of simple poles and multiple order poles you have to use a combination of both the techniques. Simple poles is quite straightforward, multiple order poles you have to take successive derivatives of this factor m of s. A combination of these two has to be adopted. And in the case of complex conjugate poles, if you find the residue with respect to one complex conjugate pole, it is enough. The second, its conjugate, the residue corresponding to its conjugate is the conjugate of that residue itself. This is one way of handling this. Alternately, as the example that we worked out earlier suggested, you can combine the terms corresponding to two conjugate poles and find out, have a quadratic denominator and find out a linear factor in the numerator, and associate this with terms of the type e power minus alpha t cos omega t and e power minus alpha t sin omega t. That can also be done. Otherwise, if you can leave them as linear terms and then find out the residues corresponding to the complex conjugate poles, find out the inverse Laplace transform of this and combine these two resulting time functions, which again yields finally the same result.